Welcome to Ask and Learn.
In this problem, a person shakes a can of drink in ice water to cool it. The mass of the ice that will melt by the time the canned drink is cooled to a specified temperature is to be determined. So we'll assume that the thermal properties of the drink are constant and are taken to be the same of those of water. The effect of agitation on the amount of ice melting is negligible, and the thermal energy capacity of the can itself is negligible. So the density and specific heat of water at the average temperature, so the average temperature is the maximum temperature 85 plus the minimum temperature of 37 over 2 gives us 61 degrees Fahrenheit. So we can find the density and the specific heat of water at this temperature. So the density of water rho is equal to 62.3 pounds per cubic feet. And the specific heat at constant volume, or at constant pressure rather, Cp is equal to 1 BTU per pound degree Fahrenheit. So those are our properties of water. The heat of fusion of water, we'll call it HIF. The heat of fusion is 143.5 BTU per pound. So we'll take the canned drink as the system. So because the system is closed, since no mass can enter or leave, the energy into the system minus the energy out of the system is equal to delta E, the change of the energy of the system. So we have heat that is leaving the system. So since it is moving out, it's a negative. So we have minus Q out is equal to the change in internal energy of the canned drink, delta U. And this is equal to the mass of the canned drink multiplied by its internal energy in state 2 minus internal energy at a higher temperature, state 1. So we can write this equation. We multiply both sides by -1, we get that the heat released by the can is equal to mc into T2, or in this case, since we multiply by -1, it's T1 minus T2. So here we have an energy balance equation for the heat leaving the can in terms of a change in temperature. So what we do first is find the total mass of the drink. And the mass is equal to the density times the volume. We assume the density of water to be 62.3, and that was pounds per cubic feet. The density of the cool drink, and we have a 12-ounce can, and we have 1 cubic foot. So we'll write this down. 1 cubic foot is equivalent to 7.48 gallons. And finally, we have 1 gallon is equivalent to 128 fluid ounces. And so all these cancel off to give us a mass of a single can to be 0.781 pounds per can. So that's the mass of a can of the soda. Now, we can go back to the energy balance equation and show that the amount of heat leaving the can Q out, remember, is mc into T1 minus T2. So that's this mass of 0.781 pounds per can. We'll suppress the units here, times C, which is 1 BTU per pound mass, times a change in temperature of 85, the initial temperature, minus 37, the final temperature, and that's degrees Fahrenheit. So we get the heat energy leaving the can, the heat transfer out of the can, to be 37.5 BTU for the can. So that's the heat transfer, or the energy leaving the can as heat. Note that we've found the heat of fusion of water, so we can find the amount of ice that will melt to cool the drink. So the amount of ice that will melt to cause this temperature change is equal to this heat transfer, this energy, divided by the heat of fusion, HIF. So this is 37.5 BTU per can over the heat of fusion for water is 143.5 BTU per pound. And so we get the mass of ice that needs to melt per can of drink to change the temperature by this amount is 0.261 pounds.